السلام عليكم جميعا. في البداية, first of all, I want to thank all of you for attending this lecture. And also I want to thank Saudi Commission for Health Specialties for organizing this webinar. Thank you so much for your valuable efforts. And it's an honor to introduce my teacher and my brother, Dr. Abdullah Abu Jami', and thank him for accepting our invitation. Thank you, Dr. Abdullah. Dr. Abdullah is a medical physics consultant and assistant professor at the Department of Radiology, College of Medicine, King Saud University. The mic is all yours, Dr. Abdullah. Thank you so much for accepting our invitation.
يعطيك العافية إن شاء الله. Just إن شاء الله share. بسم الله الرحمن الرحيم. Thank you, Mr. Ghassan, for this invitation. I'm really very pleased to be with you tonight, inshallah. في البداية نرحب جميعا في الزملاء في الجمعية ونشكرهم على الجهد الجبار اللي بيقوموا فيه بتجهيز مثل هذه المحاضرات للتغلب على الوضع اللي احنا الآن موجودين فيه، الضائقة الموجودة، ونسأل الله سبحانه وتعالى أنها تعدي على الجميع بخير ونرجع زي ما كنا وأحسن بإذن الله. Tonight we will talk about a topic which really we think it's really important for everybody who works in MRI or anybody who deal with MR images, not necessary to be a technologist, but anybody who see MR images or work with MR images, he should know at least the basic parameters of MR imaging. First of all, there are some 2 or 3 questions. I just want to know the nature of the audience. So please, we can start poll question for the first one. You will see questions. Please try to answer, so I will have an idea about the audience. So you have 30. You can start now answering the questions. Are you a radiologist, technologist, medical physicist, medical student, radiologist, technologist? You will have 30 seconds to answer. Okay, so as we can see, there are some radiologists, technologists, medical physicists, medical students, and radiologists, which is really good variety, and so that will guide us to concentrate in some topics and try not to go deeper in other topics. The second thing also, we need to know your experience in MRI. So again, I will not go deep if most of the audience are just have an introduction status. So we see the results is that make me brave to talk about some topics, which mean there's few of you have more than 15 years, which really I'll be ashamed to talk in front of those people as they have more experience. So the MRI tonight, the topic will concentrate about factors contributing to image quality. Those include image resolution, image signal to noise ratio, image contrast, image artifact, scan time. We will not have enough time to talk about artifact, hopefully, inshallah, in the future, or maybe one of the topics was image artifacts, but we are going to address the first 3 items. which we hope at the end of this lecture, inshallah, we will be able to control those parameters and try to optimize the quality of the images by trade-off of all these parameters. So if we look at this diagram, sorry for this, we will see that image or MRI images usually consist of 5 pillars, to be honest, not 4, which are actually image resolution, image contrast, image signal to noise ratio, artifact, and we have to consider as well scan time. So we can make this all good, but if the scan time is too long, this is really not what we aim to. So let us start with image resolution. Most of MR images are represented to us as a 2D planes, which is which partitioned into a grid of rectangular elements called pixels. And that's not only for MRI, it's even your mobile phone camera. It have a digital image, which consists of small pixels. The more pixels in your camera, this means it's more advanced or more, it can give you more resolution. You can detect small details. That's why companies trying to give advanced resolutions in their cameras. The intensity of each pixel represents the strength of the MR signal emitting from a region contained within that pixel. Let us see. So, for example, this is just very crowd images which I make. As you can see, the signal is bright in the middle because it comes from area in the brain which contain. Let me just take this away. Yes, that's good. So it contains a high peak signal coming from the brain, and then that translated to a bright compared to the area surrounding the brain, which there is no hydrogen, and we expect to see no signal. The signal is very less or even noise. That is represented by black. And this image, really, there is something wrong, which I can see. Usually, pixels will be represented by a single unit shade of gray. This means it can either white or black or one of the grayscale levels. So this means that this is wrong, but it's just for simplicity to show you what we mean. So usually we will not see any pixel that half of it bright and half of it dark or something like this. So usually the average signal will be represented. So in this example, we will have a dark and bright. So it will be gray, for example, and then we will represent that pixel with a gray. That is very, very essential because when we talk about resolutions, we are really concentrating about the voxel size, which we mean this square. The smaller the square, this means we can see a very tiny details in our images. So that's what I mean. This is what we say grayscale, and that is the signal which represented in the images. The highest the signal, the brightest shade of gray that is selected for that pixel. And if there is no signal at all or just only noise, we will see a very less signal, and that is represented by a black. So the size of the MR images refer to the number of pixels. The most common MR images are a grid of 256 column and 256 rows of pixels. We can see more resolution than this, but because, as we will see in our lecture, that number of pixels is affecting scan time. That's why people tend not to have a very high resolution, because that will be affecting the scan time, as we will see. Image resolution is the ability to distinguish between 2 points as separate as this and distinct. And this is an example. For example, we see this image for the first side. You see this is, for example, it's a cat. It could be tiger. It could be anything else. I mean, because the resolution is too low, we are not really confident that this is our decision. But if we have a very high resolution, as you can see, the pixels now are getting very small. We cannot see those small pixels or those small squares. And as I just mentioned, each pixel will be represented by one of the grayscale values. So either white, very black or between the grayscale levels. And if you go to there, so this means all signal within that pixel will be averaged to produce only single grayscale value. If we go to this picture, which is a cat with a very high resolution images, we can see a very tiny details in that picture. This means this is a very high resolution images, because even still we cannot see those pixels. So this first picture is taken from a camera with a very low resolution, and it was a very small object in that field. And then we want to see what is that object, so we make it magnified until this is the maximum we can see. But if we have an advanced camera, we will be able to zoom until we see all these details. Exactly what we have in MRI. If we have an image with a very high resolution, we will be able to see very tiny details in our images compared with an image with a very low resolution. Once you zoom the image, you lose all the information, and you get to the end of that image. So this is, for example, an image with a low resolution. If you try to zoom that area, you get to this. So that's the maximum you can see, and there is no much information we can get. As we get more and more resolution, we will be able to tell and see very informative details. And sometimes resolution is very important, especially if we are talking about small structures like pituitary gland, orbit. Some tiny structures, you need to have a very high resolution to see what is going on. So image resolution controlled by the voxel size. So we agreed that the small square is our final goal, or our limit. So the smaller that square, the better the resolution. Now, in MRI, since we are dealing with 3D, to say, thickness is very important. It's not like a digital camera where you take your picture and then you don't know how far that object from you or from each parts in the images. In MRI, we take like slices, or what we say, and they have a depth. Each slice has a depth. We call this a slice thickness. So instead of pixel, we will say voxel. So voxels means a pixel, but with a depth. That depth represents the slice thickness. So voxel, which is a single volume element, so small voxels result in a good image resolution, as small structures can be easily differentiated. Bear in mind that usually pixels or voxels will show the average signal within that square or cube. So it will accumulate all the signal within that cube and then represent it as a single shade of gray. So either white, black, gray, one of the gray scale. And then that's why the smaller the voxel or pixel, the better the resolution. We will not have more averages. And one of the artifacts we will usually hear about is partial volume. Partial volume comes why? Because our slice thickness is thick, and then we are trying to take average of all the structures within this voxel, and it will show like in between, not gray or bright or this. So it will show in like a cocktail of all signal within that voxel. So that's what we mean by voxel. So it is slice, a pixel with a depth. A depth represents a slice thickness. Again, as you can see, again, this is not a real images or not a real representation. As we said, pixel should usually be represented with a single gray scale value. But we can measure the pixel dimensions or pixel by dividing the whole width of the picture to the number of squares within the image. So as you can see, resolution is represented by a number of pixels. This is not a so good image because you see there is a lot of averaging there. You cannot see any details in this image compared with this image, which has much better resolution because we can see details, we can see boundaries, edges, and that all can help us to understand what pixels mean. So image resolution can be abbreviated by the voxel size, and image resolution are usually affected by slice thickness, depth of the slice, field of view, the coverage that we are going to cover in our image, number of image matrix, which is number of pixels. Field of view, usually we are all familiar with Google Maps, or so if we try to see, for example, the field of view for this Earth is huge. So we will not be able to see any details unless we go and do more and more. That's what we mean is the zoom. As you can see, the distance between the edges of your picture is called the field of view. Now, as you can go smaller and smaller, you'll get better. This is a smaller field of view and better resolution. This is our MRI unit is located in our hospital. Number of image matrix, again, it's playing a very important part in the resolution. So usually, as I said, we can calculate pixel size by dividing the field of view, which is the edges, the distance between the edges of your picture or your MRI image, by the matrix size. So matrix size means the number of pixels in your image. If it's 128, 256, so you divide the size of your image, which is like, for example, let's say 240 centimeter, you divide it by 240 or 256 pixels, and then you will get the pixel size. So our resolution usually should be represented by pixel size. So the smaller the pixel size, the better the resolution. So an X-ray or conventional X-ray, there is no limit for the resolution, not digital X-ray. I'm talking about conventional X-ray, which is the plain film that we use in old ages. Because if you take an X-ray film and just try to project it in a stadium screen, it will not show any pixels because there is no pixels. It is because it is like conventional, it is not a digital. While an MRI, because it's a digital, there is a limitation of your resolution, beside the time and what we said. Again, if we try to zoom, we will get to the point where that is the maximum. You will start to see those pixels. So usually we represent our images with resolution, and resolution can be abbreviated by a voxel size. So voxel size, which we can be calculated by dividing the field of view over the number of pixels, which we matrix size. As you can see, field of view, because it is 2 dimensions, we divide it by the matrix size, and from there we can calculate the voxel. But we multiply that by the slice thickness, as we mentioned, we will get the voxel size. Again, resolution can be controlled either by making your field of view smaller, or just keep the field of view as it is and increase your matrix size. Our final goal is to calculate the single voxel size. That is the resolution. Now, the best resolution is where you have a very high matrix and a very small field of view. This is the highest resolution you can acquire. And from there, we will see that it has a limitation. Sometimes it's not possible to have a very high resolution because of many things we will see through this lecture. So again, we should not forget the slice thickness. Usually we multiply the pixel dimensions by the slice thickness to get the voxel volume. For example, in this images, we have 2 images. The one in the left with the small field of view with the high resolution, as you can see, small field of view, but the matrix size is 256, compared with image B with a large field of view, but the matrix size is high. So which one you think it has a better resolution? Is it image A or image B or both? So we'll give you 30 seconds to answer. I will put the image back so you can see them. So you think image A or image B, or both are same, or we have something missing which we cannot decide? Okay, so most of you, they said image B has a higher resolution. Some of you, they said image A. Some, they said both have the same resolution. And a very few, they said not enough information. The correct answer, to be honest, is the last one. But those who selected both have same resolution, again, they are correct. If you divide, as we said, it's the pixel size that is controlling the resolution. If you divide the field of view, which is 125 by 256, it's like 0.5. And if you divide the field of view there, 250 divided 512, it will again 0.5. But there is something missing. Don't forget that we said thickness is very important. We don't know about the thickness. So we did not say the thickness, for example, is 2 millimeter, 3 millimeter. If this image has a thickness of 5 and this has a thickness of 1 millimeter, or our calculation is wrong. So we have to know, again, the slice thickness. So the correct answer is not enough information. We have to know the slice thickness so we can control, we can tell which one has higher resolution. So generally the field of view and accordingly the voxel dimensions is controlled by one of two parameters. The applied magnetic field gradient strength, because inside the magnet we have coils plus the magnet. It's not the main magnet coil. There are smaller coils built inside the magnet. The function of those coils is to be active during the scanning, and they're generating a linear magnetic field gradient. That means it's high in one side of the magnet and a very low on the other side. So if we switch on the magnet gradients during the scan, they will help us to select a slice or to do frequency encoding, phase encoding, and many things. So those gradients are responsible for field of view. The higher the gradient strength, the sharp the slope of the gradient. That means the field is smaller, the slice thickness is thinner. And if there is no gradient, let us say in the slice encoding direction, the gradient is 0, this means there's no slice selection. We are exciting everything. So it's actually inversely proportional to the gradient magnetic field. So the first, the field gradient, as you can see, and this is the diagram, or what we call timing diagram of this spin echo sequence. That is the gradients, the gradient pulses. So we do a slice selection gradient. This means the current will start on for some time and then turn off. So the highest means the higher current goes to those coils during the excitations, mean the thinner the slice. Again, in the two gradient, which are X and Y, let us say in one example, if I am acquiring an axial slice, that phase encoding, frequency encoding, the higher the gradient, the more current goes to those gradient coils, means the smaller the field of view. As you can see, it can be strength or duration, means what we are interested is the amplitude, total amplitude of that gradient. As you can see, the smaller. Or it can be amplitude, that means the higher current going to the smaller. So it's inversely proportional to the strength of the gradient, applied gradient. The other important thing is the bandwidth, which correspond to the time, as we just showed there. Let's go to the previous slice. Bandwidth means the duration. If you're, this is the bandwidth in that case, and the bandwidth there in that case. But usually in MRI systems, they tend to just increase the strength of the current. This is more stable. So if you want smaller field of view, they will send more current to the gradient. If you want a larger field of view, they will reduce the current that goes to the gradient coils. So again, as I said, it depends on the strength of your gradient. As we have sharper gradient, means the strength or the slope of your gradient is higher. This means that your slice thickness will be thinner. And if you have a shallow gradient like what we see there, your thickness will be thicker. If there is no gradient at all, this means you are exciting everything. There is no thickness, and you will have a slice thickness of infinity. So again, voxel size is generally controlled by number of RF pulses, type of radio frequency coil, or strength of the gradient magnetic field, or strength of the main magnetic field. So which one you think it is affecting voxel size. Okay, so we have majority is selecting the strength of the gradient, which is actually correct, because number of RF pulses has nothing to do with the slice thickness or field of view. Number of RF pulses will generate the sequence, but it has nothing to do with the resolution. Type of the radio frequency coil, it has an effect on the signal to noise ratio, as we will see in the second topic. But strength of the gradient magnetic field is the one which really make the field of view smaller or larger, make your slice thickness smaller or thicker. Strength of the main magnet, again, will not affect the resolution. It can be used to produce thinner slices because it gives you more signal, as we will see again in the signal to noise ratio. So image resolution, on the other hand, the number of image metrics can be increased by sampling more points in the frequency encoding direction and applying more number of gradient field steps in the phase encoding directions. For example, if I have a spin echo sequence, the more number of phase encodings, I mean, there was a lecture maybe 2 or 3 weeks ago, we talk about how to generate an MR image, or how MR image is optimized. But just to make it quick, MR image is generated usually by combination between radio frequency and a gradient, magnetic field gradient. So we excite the protons to turn the protons from z-axis to the xy plane. During that, slice electric gradient is applied to restrict your excitation to a slice rather than exciting everything, as we just mentioned. So the slice electric gradient makes your slice thinner. And then, for example, it's 2 millimeters, 3 millimeters. It depends on the strength of the gradient that is slice electric gradient, applied gradient. And then we will apply the phase encoding. Is like if you have an area, it's the number of streets in your, and then at the end we will do, and then first 180 to refocus the protons, and then we collect our echo. And from there we can get our image as a result of the, so a number of samples, as we see in the frequency on the readout and the readout gradient. So the smaller the sample size, the better the resolution. Usually I just represent this by, if you have a class with 100 students and you make a quiz for them and you make your degrees, for example, those people who get from 100 to 80, they will get A. And anybody who gets from 80 to 60 will get B. One student who gets 100, he will come to me and shouting and said, how do you make me like the one who gets 80? I studied a lot and then I get the maximum score. And that one who just studied 5 minutes before the exam, he get 80, both of us get A. So this means it's unfair. So I need to make it's more resolution, means more accurate representation of my results. So the more samples, I mean, the more number of samples or smaller sample size, that makes your resolution better. So instead of having, for example, 64, you go to 128 or 256. So the more number of samples, the better the resolution. And we will see that in the phase encoding direction, this is really affecting scan time. So for example, if you get there like 128 line in your image, it's different. The time will be doubled if you have 256 lines in your image. So this is one of the obstacles in the resolution, that we cannot go very high in our resolution because it's directly affecting your scan time. So this is how MR image is acquired. It's like a repeated process. You acquire 90, 180, then get a new key. And then you go excite again, similar, but with different phase encoding, with different gradient strength, as you can see. This is repeated like 128 or 256 times. After each acquisition, we have to stop for a time. It's called repetition time. That is very essential to allow the protons to recover and start excite again and again until you get the max, the full Fourier space or full Fourier image information. Okay, so which of the following has no effect on image resolution? So is it TR and TE or field of view, slice thickness, image matrix? One of those has no effect on the image resolution. So the correct answer is 1, because the T and TR, they are affecting image contrast, how that signal is in each pixel is represented. Just quickly, we can refer to any signal can be represented by either its amplitude or phase or frequency. So amplitude is actually representing the contrast, which has a relation to T and TR. But phase and frequency, usually we use them to produce the field of view and slice thickness and again image matrix. So all of these are affecting image resolution except T and TR because they are only affecting image contrast. Okay, now we will come to the second part. Resolution was one of the important parameter of MRI image, but signal to noise ratio again is another important parameter that it's good to have a very high resolution image, but if you have a very high resolution image while your image is very noisy, this is not really so good. So if, for example, let's see this example, that is usually what we say is the noise. For example, you see those white dots in your image, this is the noise, and this is the real image. So what we see normally is image plus noise. Since MR is an electromagnetic waves, it's anything applied to electromagnetic waves will be applied to MRI. You radio in your car when you travel with your car and then you turn your radio, sometimes you can hear some voices, noise. That is the background, which comes from many things. And when the speaker talk, this is the signal. So what we hear usually is the speaker talking plus the noise in the background. And if that noise is higher than the voice of the speaker, we will not be able to hear anything. This is apply exactly in MRI. Noise is the background of our image. It has many sources, as we will see. And image is the MR signal, which is represented by the signal that we pick from the patient. What we see at the end is image plus noise. Our goal is to make the image like this. So trying to reduce the noise and maximize the signal. So the final goal is to have a very high signal to noise ratio. We cannot measure the noise itself because it's random. And signal, again, it's arbitrary. So we cannot say our signal is 100. 100 compared to what? I cannot say this signal is good unless I compare to something. If I say our signal strength is like for 10 or 20, it's so good. So good compared to what? We have to have a reference. So they agreed that we measure the signal compared to the noise. The higher the signal compared to the noise is that the better the image signal to noise ratio and the quality of your image. So in MR imaging, there are two major contributions to image noise. First, the patient himself is the source of signal, but again, it's the source of noise. He's again a source of noise. So the random motion of charged molecule in our body produces electromagnetic noise, so which we call them Brownian motion. So electrons moves in our body, the tiny charges can be picked by any antenna or coil. If you put a voltmeter or meter in your hand, sometimes you can measure some tiny current. That is really we call it's a noise, or that will contribute to the MR image at the end. Again, there is some noise comes from the wires or coils or capacitors, resistance, all these devices which the signal travel through at the end, contributing to the noise. So if I, for example, say this is an image, patient is a source of noise. He's the main source of signal, but unfortunately there is some noises coming with that signal. Again, when the signal is picked by the RF coil, the coil has a resistance. That resistance translated as a noise. The wires which deliver the signal from the coil to the preamp, it has a resistance, which means noise. The preamp itself, which process the signal, it has a noise. So it's like an accumulated series of noise. At the end, you will get the signal, which has a source from the patient, but adding to that, there's a series of noise, which really affect your quality of image. So this is what, for example, a simple signal, MR signal. So that is the noise, which is random, and that is the MR signal, which comes from the hydrogen, which come from the patient. So usually we measure signal to noise ratio by dividing the signal strength by the noise, which is, for example, 100 dividing 5, the signal to noise ratio will be 20. This is an example. If for simplicity, I take a ROI, region of interest inside the brain, an area with a tissue, and then I take the same region outside the brain, which we are sure that there's no signal, it's only noise. And then divide the signal strength there is 700, and the signal there is 20. As a result, the signal to noise ratio will be 35. This is compared to a very noisy image where I take the square, for example, outside. You can see that those dots is actually noise. If I divide the signal within the brain by the signal outside the brain, it's actually 300 divided 50, which is 6. And from there, we can say that which one is having higher resolution, has higher signal to noise ratio. This image has higher signal to noise ratio. So the signal to noise ratio can often be improved by a proper selection of a receiver coil. Now we will go through the journey of signal to noise ratio, see how we can optimize the signal to noise ratio. First step toward the signal to noise ratio, before even the receiver coil, is the magnetic field strength. This is one of the basics of theory of the NMR. Field strength means the magnet strength. 3 Tesla, for example, producing net magnetization 4 times the signal strength produced by 1.5. So the higher the magnetic field strength, the more signal magnetization, and that means more signal. Although the noise is almost random, will not change, but we will have better signal. So signal to noise ratio at the end will be again better. So first step is to have a higher magnet strength rather than having 0.5 Tesla magnet or 1.5 if you can go for 3 Tesla. But this is 3 Tesla has again disadvantage. It's not the place to talk about this, but the field strength itself has an important effect on the signal to noise ratio. Let's say in our hospital we have only one magnet, which is 1.5. Now the second step to go is selecting the radio frequency antenna, the radio frequency coil, which is going to pick the signal from the patient. And as we can see, there are a variety of coils. And there are coils designed to pick the signal from head, another one from knee, from wrist, shoulder, for example. This is MRI for breast, and this is for abdomen or cardiac. And there are small coils for fingers. again, this is for ankle. Why should we have different coil? Why I should not use, for example, that coil for everything? RF coil is, although it is an antenna that picks the signal, but again, it has a component inside it. If I open that coil, I will see inside that coil circles. Those circles consist of wires, capacitors, resistance. All these are additional sources of noise. So the smaller the coil, as you can see that one, the better the signal to noise ratio, because there's not too much contribution to the noise. The resistance of that coil is very minimum, and accordingly the noise will be less. The other part, I cannot use this for the brain because it's small. I have to have a large coil to cover the brain and to have sensitivity of every part of the brain within that coil. So just to know that, that's why we have different coils. So the smaller the coil that can accommodate the anatomy that you are going to scan, the better. And there are many other things which I'm not going to talk about because this is all instrumentation engineering. But let us say the smaller the coil size, the better signal to noise ratio. That's why the new technology tend to have coils with multi-elements or multi-channels. So they say the phased array coils. Within that coil, you will have a smaller coils inside the main coil. So we call them channels, for example, or elements. In this example, we have an 8-element coil. Each element is represented by one coil. As you can see, the signal is high from there, and that signal is high. At the end, we will accumulate all of these images to produce the final image. So this is called the phased array coil. And this is another example. We have like 6 elements. At the end, all this will contribute to produce your final image. This is an example, a research coil, which contains 96 elements to produce the better signal to noise ratio. So the signal to noise ratio in MR depend on the amount of signal from pixel or voxel. The signal to noise ratio is proportional to the voxel volume. Now, this is 2 images, one with a voxel size, let us say 1 centimeter by 1 by 1. So 1 by 1 by 1. This is 1 by 1 by 2. So the thickness of this slice is double the thickness of that slice. So usually we will have double signal to noise ratio in this image compared to that one. Since, for example, if we have a 1 million proton within that voxel, this means we will have 2 million proton within that voxel. So increasing slice thickness, or let's say increasing the voxel volume, will directly proportional to the signal to noise ratio. So that is the voxel. As we agreed, field strength is the first tool to have when you want to do high resolution. So for example, if you have a clinic or a hospital that's interested on, let's say, ENT, for example, or a small high resolution sport center, for example, they usually want to see a very tiny details. So we will advise them to go for 3 Tesla because they need to see a very small details and very high resolution. While in 1.5, as you can see, signal will drop according to that. Let's say we have 1.5. Now, field view means we agreed that the voxel volume is our directly proportional to the signal to noise ratio. So the larger the voxel size means more protons within that voxel, and accordingly more signal to noise ratio. If I make my field view smaller, means I'm trying to push or squeeze those voxels, and accordingly the number of protons within each voxel will be less, and the result will be less signal to noise ratio. Matrix size. Matrix size means within the same field view. Let's say I have a fixed field view. If I increase the matrix size, and instead of 256 by 256, I make it 512 by 512. This means number of pixels within the field of view will be more, and the voxel size will be smaller, and accordingly the few protons and less signal to noise ratio. Slice thickness, as I said, The smaller the slice thickness, fewer proton and less signal to noise ratio. While the higher the slice thickness, or the thicker the slice thickness, you will have more protons and more signal to noise ratio. As you can see from there, that everything we do there is affecting resolution, signal to noise ratio, but on the other hand, also affecting the resolution. For example, if I make my field of view higher, correctly, I will get better signal to noise ratio, but I'm losing my resolution. Matrix size, as I make my matrix size smaller, it's excellent signal to noise ratio, but I'm losing my resolution. So it's not a single man show. It's like a combination for many things. You have to consider field of view, matrix size, slice thickness. All these has to be considered when you decide your image parameter. Don't forget that those directly affecting image resolution. As we said, signal to noise ratio, field strength can play a factor, RF pulses, RF coils, voxel volume, number of lines in your image, and the receiver bandwidth. So this is an example of field of view with the brain with the large field of view, and this is a brain with a smaller field of view. As you can see, those white dots are the noise that we are mentioning. The smaller the field of view, you will have more and more white dots, which is actually the noise, what we refer to noise. So which of the following is expected to increase image signal to noise ratio? Decreasing the slice thickness, decreasing image matrix, decreasing the field of view, or decreasing the field strength. So increasing SNR, how will you increase SNR? Okay, so we have like average answers. Let's start with decreasing the slice thickness. As I said, decreasing the slice thickness means less number of protons. And this is what you don't want for the signal to noise ratio. We need more number of protons. So by decreasing your slice thickness, you will have a few number of protons and accordingly less signal to noise ratio. So this is wrong. Decreasing image matrix. Image matrix was like 256 by 256. So our squares, bear in mind, within the same field of view. But if I decrease my image matrix from 512 to 256, the matrix size, the voxel size will get larger. This means more proton within the same voxel or pixel. This means better signal to noise ratio. So decreasing the field of view, by decreasing the field of view, again, I'm squeezing those pixels. By squeezing them, making them smaller, there'll be few protons within the pixel or voxel, and accordingly, signal to noise ratio will be less. Decreasing the field strength, this is unwanted. For example, 3 Tesla, we said much higher than 1.5. 1.5 will produce a net magnetization of signal much higher than 0.5. So the correct answer is the decreased image matrix. So generally, signal to noise ratio is proportional to the voxel volume, as we agreed. So the smaller the voxel volume, the less signal to noise ratio. The larger the voxel volume is the higher the signal to noise ratio. And also proportional to the root mean square of NIX. NIX is number of averages, number of acquisitions. Sometimes they say number of acquisition. We mean by number of averages, sometimes you get the signal once, the reading of your signal, the acquisition once, but because it's too noisy, you need to improve it. So you repeat again the same acquisition 2 times or 3 times to take the average. So it's number of averages or number of acquisitions, number of citations, all these names for the number of NIX or number of averages. But it's actually proportional to the root mean square. Why root mean square? We'll see now. This is 2nx. That is the MR signal, and that is the noise. If you take 2nx or 2 averages, signal, since it's coming from a place which has a hydrogen, its signal is known to have that strength. But noise is, as we agreed, it's random. Sometimes come from resistance, sometimes come from temperature, from the patient, Brownian motion, many things. It's actually random. So in the first acquisition, that was the noise. In the second acquisition, if we try to accumulate the signal, in this sense that was, and then this is a peak, if you add, they will cancel each other's. While in this situation, both are high, so they will add to each other's. So at the end, they say the signal will be duplicated, that's true, but the noise will not be canceled. It will be increasing by the root mean square of the averages. That's why we said it is proportional to the root mean square of number of. So in this case, if I take 4 averages, I will be only improving my signal to noise ratio by 2. And if I take a 10 averages, I will improve my signal to noise ratio by only 3.2. So 10 averages means multiplying your scan time by 10. So let's say if you have 4 minutes sequence, that with 1 average, if you take it 10 averages, this means you multiply 4 by 10, this means 40 minutes for single series, and this is not acceptable. So averages is not the easiest solution or the best solution to improve your signal to noise ratio. You should keep this to the end after you utilize all your resources from matrix size, field view, field strength, selecting the right RF coil. And I'm insisting on this because selecting the coil is really sometimes is the best way to improve your signal to noise ratio. After you utilize all these things and then you reach to the point still noisy, then you go for increasing your averages because they will not actually increase your image by double. They will just increase your image by a root mean square of the number of averages. So as you can see, this is one average, 2 averages, 3 averages, and the more averages you see, the noise will be almost. So let's summarize that. Factors affecting signal to noise ratio. First, strength of the main magnet. As you can see, for example, this is acquired at 1.5, and this is acquired with 3 Tesla. Resolution and signal to noise ratio is better. And another example, as you can see, those 2 images acquired with 1.5 and 3 Tesla. All other parameters are the same, exactly the same. So as you can see, the one acquired with 1.5 has a lot of noise compared to the one acquired with 3 Tesla. Those white dots that we are mentioning is actually very less compared to the one in 1.5. So 3 Tesla is the choice if you want to see a very tiny details. They will give you a better signal to noise ratio. And when you're trying to improve your resolution, still you have signal that can support you. Coil selection, as I said, it's very important to select the right coil for your study. Voxel size should be selected reasonably. I mean, depending on your target resolution, depends on the type of the exam. Are you going just for a brain screening or spine screening, or you want to see a very fine details like in pituitary gland or epilepsy, for example, protocol? You need to have a very high resolution and accordingly you need to go for a smaller voxel size. Number of phase encodings, again, number of metrics that is affecting your signal to noise ratio. And again, number of averages, I say this should be kept to the end because it will just proportional to the root mean square of the averages. One more important parameter is the receiver bandwidth, again, which we mentioned earlier. Receiver bandwidth is an important tool, actually, we can use to improve signal to noise ratio, but it has, again, complications. We have to be careful of that. It's not actually free of charge. It's selecting smaller bandwidth. So normally we select a moderate bandwidth, but if you select a very high bandwidth, this is the MR signal, and that is all remaining is noise. So what you acquire there is signal plus a lot of noise. If you try to make your bandwidth smaller, so you select, for example, this, now you get signal plus still some noise, but we try to make it very small, so you will only acquire the signal. This way you cut part of your signal. To represent this, I just make some PowerPoint, some presentation, which is not a very good drawing. But as you can see, if you are in a room, for example, that has a tree outside, you can, from your window, you can see that tree, but unfortunately people, they are throwing their garbage surrounding that tree, and you don't want to see this. So you decided to close your curtain. So by closing your curtain, you cut the noise. But be careful, because you cut also part of the branches of your picture, with your tree that you want to see. For example, this is very nicely, no rubbish they're showing in your picture, or from your view in your room. But unfortunately, your image is not complete because you cut part of the branches, and that will affect the complete picture of your image. It's exactly the same for bandwidth. Be careful. Reducing the bandwidth too much will produce an artifact called truncation artifact. Means you truncate your signal, and then like lines in the image will be shown, and that is the artifact called truncation. This comes from the bandwidth. Plus other things also reducing the bandwidth. It has a problem with a chemical shift artifact, producing, for example, a susceptibility artifact. All these are complications of reducing receiver bandwidth. So we have to be careful using the correct receiver bandwidth. Pulse sequence parameters, they are very important, like TR, TE, type of sequence, all these affecting signal to noise ratio, number of averages, and other things always play an important tool in your signal to noise ratio. So first of all, we said the field strength is very important. If you decided to buy 3 Tesla or 1.5, and then you go for the other parameters, field of view, they will improve your, reducing the field of view will improve your resolution, but you will lose your signal to noise ratio. Matrix size, slice thickness, number of excitation or averages is very important. And then bandwidth is again important. So question time, reducing receiver bandwidth will directly improve which of the following? Will improve image resolution, or image signal to noise ratio, image contrast, or scan time. All right, so reducing receiver bandwidth will directly improve your SNR, which is correct. Some people, they say it can affect resolution. It's actually, it will not affect your resolution, but it will help your resolution. So it is like the product of the bandwidth is, for example, if you have an image, you want to do a very high resolution images, then you think about reducing receiver bandwidth to improve your SNR. Image contrast, it has, I mean, nothing to do, it has a list, but it's not actually improving your contrast. Scan time, again, it's not directly affecting, I should mention there directly, because sometimes it can affect by increasing number of slices, but directly it's not affecting your scan time. So stronger, to improve your signal to noise ratio, you need a stronger magnet, proper imaging coil, larger voxel size, decrease phase encoding, increase number of averages, decrease receiver bandwidth, and then select the appropriate pulse sequence. Last topic in this lecture is the image contrast. Image contrast, again, is the third pillar in our image quality. So if you have a good image resolution, a good image contrast, but at the end, you cannot see any difference between the tissues, so this is useless. To have a very good MR image, you need to have a very high good contrast between tissues, so you can represent, or between normal and abnormal tissues. As we mentioned at the beginning, the pixel image brightness is directly proportional to the MR signal strength from that pixel. As we just mentioned, it's, for example, if that part of the brain contains CSF, which have a huge number of proton in that area, means the signal is high, and accordingly you will see that's bright. So it's actually proportional to the signal strength from that pixel. And that will be translated by the grayscale, as we mentioned, to produce the final MR image. To distinguish different tissue and MR images, each tissue must possess different brightness. This concept is expressed in term contrast. So as you can see, for example, why that signal coming from ventricle is bright compared to the surrounding of a gray matter is dark. Because the signal strength, the final or the total signal strength from that part of the brain producing a very high signal, and that is translated to a bright in the image. MR considered one of the best modalities in radiology to display anatomical structures, like in pelvis, for example. You can see different structures within the anatomy there. Again, pillary ducts can be seen clearly without any need to use any external contrast. Again, in the pelvis, you can see a different layer in the uterus, for example. Many things, for example, the white matter changes in the brain can only be seen by MRI. If you do a CT scan for this patient, it will show nothing. It will show normal, but because MR has an ability to show the different contrast between affected lesions, affected part tissues in the brain and the normal tissues, it has a unique value in radiology. So again, bone metastasis, bone marrow, again, edema, fatty liver, stroke, angiography, all these can be seen very nice, or can be represented very nice in MRI. So a number of factors affecting MR image contrast. They can be divided into two basic groups. Internal factors, which include tissue parameters like T1, T2, proton density. And there are then external factors which represent, we call them operator-dependent parameters, which can be controlled to highlight a specific contrast. And those are namely TR, TE, flip angle, inversion time. All these parameters are operator dependent. So when we set up an exam, we select a TR, TE, flip angle to highlight the contrast, the desired contrast that we want to see. So for example, TR and TE can be selected to make your image have different contrast. Now, the signal strength of a given tissue is proportional to the product of three weighting terms. So the final result of your signal strength is actually, it's a product of three weighting terms. So by weighting, we mean the influence of a given term of image contrast is dominant. And this can be expressed in this equation. So in spin echo sequence, it can be written in this, for example. So signal equals proton density, which contains a number of protons within a single volume element, for example, or space. And then we have a T1 weighting term. Within that term, we have TR, which is an external parameter, and we have a T1, which is internal. That's related to the type of tissue, and this is selectable. So it means the operator can select the TR to highlight a specific contrast. Then we have a T2 weighting term. This means we have, again, two parameters, one external and one internal. Internal is T2, which again relate to the type of tissue. Is it have a short T2 or long T2? Again, a TE is an echo time, which is controlled by the operator. He can select a TE or TR that matches his image contrast. So from that equation, we can select TR and TE to highlight a specific contrast. Now from that equation, I can make, for example, mathematically, we can make that term equal 1, or that can equal 1. So the signal will be proton density. So if I want my final result of my image to be a proton density image, I have to make that term equals 1. And that term equals, so it's signal equals proton density. Now, proton density is always there because it comes from the hydrogen. If you have a tissue with a higher number of protons, that means you will have higher signal if you have all these parameters again selected correctly. But if there is no protons, for example, in air or in bones, there's no hydrogen, and that will be black. Whatever you select TR and TE, the final result will be 0 because that is 0. So multiplying by anything will be 0. So that is the equation that we have to think about when we make our contrast. So usually our MR images will be displayed, or the contrast of our images will be depending on your T and TR. So it can be like a T1 where a fluid is dark, or it can be T2 where a fluid is bright, or it can be a proton density with a fluid like a CSF is iso-intense. For example, if we want to produce a proton density weighted images, we have to diminish the effect of other two factors. And we have three factors: proton density, T1 and T2. If I want to produce a proton density image, I have to diminish the effect of T1 and T2 term. T1 and T2 can be diminished by appropriate selection of T and TR. So by making TR and TE short, that will produce you T1 weighted images. If you select a TR and TE high, you will get a T2 weighted images. This is an example of images. For example, TR, if we select a long TR and long TE, that will be a T2. Short TR and short TE will be a T1, long TR and short TE, that's a proton density. So a question: which of the following has no effect in image contrast? TE and TR, type of image sequence, tissue parameters such as T1, T2, proton density, slice thickness. Okay, so we are talking about image contrast. So we expect, we said no effect. Which one of the following has no effect? So T and TR, they are external parameters and they are directly affecting image contrast. Type of sequence, we have like a spin echo, fast spin echo, gradient echo. These will affect image contrast. Tissue parameters like T1, we call them, this is internal parameter or tissue parameters. They are directly affecting image contrast. Slice thickness, it will affect resolution, signal to noise ratio, but will not affect, in general, will not affect your image contrast. So we will concentrate now on different type of contrast or image contrast in MRI. We usually hear T1 weighted images, T2 weighted images, proton density weighted images, and so what does that mean for us? A T1 weighted image is one where the contrast depends predominantly on the difference in their T1 times between two tissues. You remember in our school, when we were in the school, we have different maps. So for example, in geography, we have population map. It will show areas with higher population with red and the areas with low population with green, for example. And we have weather map, which shows, for example, those cold areas with the blue and those hot area with red. So each map represents something. If I look to the population map, I will not be easily any correlate this to the weather type, or to correlate this with the let's say, for example, how any the shape of the is it high from the earth, or from or just near the sea. So each one of those maps, it's concentrating on one type of information. So if I say T1 weighted images, this means it's concentrating on only T1 information. Means that it only reflects the difference between tissues according to their T1 values. And T1 weighted images is produced usually by controlling an external parameter, as I said, which is a TR. TR controls how far each vector can recover before it is excited by the next RF pulse. So I try to draw this. For example, I have tissue A and B, let's say fat and water, or CSF. Now, after each excitation, we know fat is recovering so fast. So if I wait too much until both tissues, fat and water, recover, I will not be able to tell which one is faster. For example, there I say I have two runners. One is fast and one slow. So I said I will go 5 minutes and then come back. When I come back, I'll see who reached the line. When I come after 5 minutes, I will find them both. They already reached the final line. But if I come after 30 seconds or 20 seconds, I will be able to see which one is faster. So for example, in this example, I need to select the maximum difference by selecting a short TR, not a very long TR, because this will allow them both to reach to the end. And this can be seen in this diagram. So this is immediately after excitation. Still, there's no time for the protons to recover, and the image will become usually dark. Only vessels will be bright. As I increase my TR, I'm allowing some tissues like fat to recover, and some like fluid CSF is still in the near to the transverse, and it will show black. But if I give more time, I will see that all protons recovered and all tissues there will appear same, because they already recovered, and the contrast between the tissues is actually almost nothing. So this is very important. TR is the key factors or the key player to produce your image contrast. So no, that's not playing. Okay. So to achieve a T1 weighted images, TR must be short enough, between 300, that's in spin echo and fast spin echo. It should be selected between 300 and 800 milliseconds, so that no one of the two tissues magnetization has sufficient time to fully return to B0. If a TR is too long, both tissue return to net B0 and recover their longitudinal magnetization fully. When this has happened, T1 relaxation is complete in both tissues, and the difference in T1 times are not demonstrated in the image. So normally we use, again, a short TE values. Why? As you remember in that equation, we try to diminish the effect of T2 term. And that T2 term mathematically can be diminished by selecting a short TE values. Short means between 10 and 20 milliseconds. That will make that the term of T2 equals 1. And accordingly, it has no effect on your image contrast. So usually we need to get rid of dephasing in the image, because T2, actually, the more T2, the more dephasing, and the more T2 contrast in the images. So reducing your TE will make your image more T1. And so this is an example. This is with a short TR, and that is with a long TR, as you can see. That is in 3 and 30 milliseconds echo time. T1 weighted images are useful to demonstrate anatomical structures, since they produce images have a higher signal to noise ratio. So usually we use them to show anatomy or to post contrast with additional contrast injection. Usually fluid appear dark in T1 weighted images. Since the T1 is too long, as we just mentioned, CSF takes too long to recover, and accordingly, if you select your TR short, CSF have not sufficient time to recover and will not show in the images. So fat tissue, on the other hand, will appear usually bright in T1 weighted images because fat is very fast in the recovery. The fat has a very short T1, and usually we will see fat always bright in T1 weighted images. So in T1 weighted images, CSF is black, fat is white, gray matter is dark gray, white matter is light gray. And this is an example of T1, sagittal T1 weighted images. And this is an axial T1 weighted images. So this is an example of tissue appearance in T1 weighted images. And as I said, air cortical bone usually is black. Why? Because there's no hydrogen. So proton density is 0. 0 multiplied by all other parameters, all other terms will be 0. And other tissues will be bright or dark according to their type. So our question, fat tissue appears very bright in T1 weighted images because it has a very long T1 value. Fat has a very high proton density. Fat has a very high, very short T1, sorry, and fat has a very long T2. Which one do you think the correct answer? Okay, so we can see that the majority they selected, fat has a very short T1, and as I said, because it has a very short T1, it will recover fast. So when we come to excite the second line on the image, there will be more and more number of protons from fat, and that's why fat usually appears bright in the T1 weighted images compared to the CSF and other tissues. Now, T2 weighted images. A T2 weighted image is one where the contrast predominantly depends on the difference in the T2 times between two tissues. So now we are not measuring the recovery, we are measuring the dephasing. So in the transverse plane after excitation, protons tend to dephase, to go out of phase. So what we are measuring is how fast those tissues are dephasing. So this is called T2. So the important parameter, or the key factors, the key important parameter that measures this is the echo time. The more echo time you give to the protons, the more dephasing. So you can see which one is dephasing fast and which one is dephasing slow. So TE is a key factor. And this is an example. So 90 degree, the protons, they will fall in the transverse, they will start to dephase. And then you get a refocused RF pulse, and then you collect your echo. So the more TE, you see, the more dephasing, and that can show you better contrast based on a T2 weighted contrast. Again, this is another example. I just try to make it clear. We have two tissues. If, for example, I select a TE of 10 milliseconds, which tissue you think has more, dephased more? There's no enough information because I cannot see. Still, they are just start to dephase, and from there I cannot tell which one is dephasing faster. But the more time I give, I can see that tissue is dephasing faster, more and more. The more time, the more dephasing. And for example, at this point, I can see that tissue is completely canceled because every proton is canceled by the opposite proton compared to the other one, which still has some component. So as a result, that will show black in the image, and this will show gray. If I have another tissue with a very short dephasing, it will show bright because it's still complete intact, completely intact. So TE is the main key factors for measuring the T2 weighted T2 weighting in the image. To achieve a T2 weighted images, the TE must be long enough. So we have to make our time, the allowed time for dephasing, which is the echo time, long, so we can see which one is dephasing fast. And spin echo, usually we say between 80 and 140. It will give us good T2 weighted in the images. If the TE is too short, no one of the tissues have sufficient time to decay, and therefore the difference in the T2 time are not demonstrated on the image. Normally long TR values, as we mentioned in the beginning in that equation, we have to diminish the effect of T1. How that is diminished, how that is reduced by making TR long. So we make sure after each excitation, all the protons go back to 0 and we start fresh. So to do that, TR has to be long enough. Long means that more than 2000. Again, that's in a spin echo sequences. So as you can see, this is a TE of 30 milliseconds and the TE with 80 milliseconds. Now the T2 contrast is much better in the T2 weighted image, and the one image with the higher echo time. So T2 weighted images are usually useful to show pathology. Tissue that are diseased generally have more fluid around them. They are edematous and they have increased water content, and consequently they have higher signal on a T2 weighted images and can therefore be easily identified. That's why we look to the T2 images first to see if there is infection, edema, and from there we go and see other images like post-contrast and so on. So usually fluid appears bright in T2 weighted images since the T2 is too long. Since T2 is too long, and accordingly more number of protons will be available during echo acquisition, even if long T is selected. On the other hand, muscle tissues will appear dark in T2 weighted images since T2 is very short, and accordingly less number of protons will be available during echo acquisition if long T is selected. For example, there we can see dark CSF as we just mentioned. Again, that's T1. We should concentrate on TR. By selecting short TR, we will be able to produce a T1 with images. T2, we concentrate on TE, should select long TE, and that's producing a T2 weighted image. Again, a T2 weighted image usually produce CSF with a bright signal. Fat usually light gray. Gray matter is light gray, white matter is dark gray. Again, this is how tissue will appear. Again, as I said, air and bone, cortical bone will show black because there's no proton, and proton is 0, multiplied by other parameters, other factors, total will be 0. This is an example of T2. One thing I have to mention is that sometimes we increase our echo time more than 140. So for example, in some liver imaging, we use 250 echo time or even higher. This is used sometimes to make it, we call it a heavily T2. So heavily T2 means dephasing everything and just showing fluid. And that is really helpful if you want to see a cyst, or sometimes in MRCP imaging to show the fluid and bile duct. We select a very long TE to make everything dark or everything dephasing and just show the tissue with the fluid. Lastly, proton density weighted images, it's produced by, again, eliminating the effect of T1, eliminating effect of T2, so the remaining will be image with the proton density. So a proton density image is one where the difference in the number of protons per unit volume in the tissue is a main determining factor in forming image contrast. So proton density weighted is always present to some extent because it's the background of the image. It's either to show proton densities alone, or we can put a T1 over it, or we can put T2. If I remove a T1 and T2 effect, it will show a proton density. So in order to achieve a proton density weighted images, the effect of T1, T2 contrast must be removed so that a proton density weighted can be dominant. How to remove a T1? We have to select a long TR. We have to allow the proton to recover fully before exciting the second line, means selecting a long TR. And how we eliminate T2 effect by selecting again a short TE. We will not allow tissue to dephase, and accordingly we will be able to see the signal without T2 dephasing. So the final result will be a pure proton density weighted image. Proton density is one of the images that usually used by musculoskeletal imaging because it has a good image contrast between different structures in the body. So again, that's the chart. So short TR and short TE producing a T1 weighted images, long TR, long TE will produce T2 weighted images, long TR and short TE producing a proton density weighted images. Again, that's an example showing the CSF, how it looks in the T2, how it looks in T1, and how it looks in a proton density. So if I select my TR too short and the long TE, I will get an image something like this. So I'm not getting first enough signal recovery because my TR is short. So I'm losing a lot of my signal. Again, by using a long TE, too much dephasing. So I'm losing signal from both ways. And that's why image look like this. So it's not really useful. So this is comparison between T1 and T2 weighted images. So this question, to generate a proton density weighted images, we should use which of the following: long TR and short TE, long TR and long TE, short TR and short TE, or short TR and long TE. Which one do you think is the correct answer? Okay, so the correct answer is long TR and short TE. So long TR will allow proton to recover, and short TE will not show a dephasing and eliminate the effect of a T2 in the image. Last topic today is image contrast in gradient echo sequences. We talk about the contrast in spin echo, but how that will be different from gradient echo sequences. We know in a gradient echo sequence, we have additional parameter plus T and TR. We have something called flip angle, because in gradient echo, flip angle is not always 90. In a spin echo, we have 90, 180, and then acquisition. In a gradient echo, sometimes we have flip angle of 30, 60, or 90. So flip angle is the variable parameter in a gradient echo sequence. It's not like in spin echo. So in a gradient echo, TR and flip angle, they play an important role in controlling the amount of T1 relaxation that has occurred before the next RF pulse. So I usually just make an example of flip angle with the previous example. If I have two runners, they start, I told them you have 100 meters to go through, and only 60 seconds or 30 seconds. The time is TR, and the distance is the flip angle. So I cannot make the distance like 1 meter, because 1 meter, they will just start, by starting only, they will reach the last point. I have to give a large distance, or large, they cover 100 meters or 200 meters, and to see which one is really faster. So we have TR and flip angle, both are an important parameters in T1 weighted images. In TE and T2 weighted images, T again is the playing factor. So if I select my TE long, I can see more dephasing, and accordingly I'll be able to see better contrast. So apart of the added variable of flip angle, the rules of weighting in a gradient echo sequence is exactly the same as in a spin echo. So long TR, long TE, that's mean T2. Short TR and short TE is T1. Long TR and short TE is a proton density, but now we have flip angle. Keep it in mind, flip angle is a distance. So to see which which proton is recovering fast, I have to give larger distance, mean larger flip angle. So if I want to see a T1 weighted images in the gradient echo sequence, flip angle should be more than 60, 70, and so on. If I want to make a T2, just make the flip angle short, and the other parameter will be same as spin echo. So in gradient echo, to produce a T1 weighted images, the flip angle is selected to be large, 60 or 70 and more, and TR short. You see now, short is different than short in a spin echo. We said less than 100 is short because the gradient echo sequence is designed to make the scan time faster. Using a short flip angle, make the proton recover fast, and then the scan time will. So usually we use a TR of hundreds, not thousands like what we use in a spin echo. To obtain a T2, we call it a T2 star weighted images. In a gradient echo imaging, the TE is selected to be long between 15 and 25, so that two tissue vectors have time to decay sufficiently. Again, to obtain a proton density weighted images, the TE is selected to be short, from 5 to 10 milliseconds, and the flip angle is small, as opposite to T1. And by that, we will be able to use to produce a proton density. So diminishing the effect of T1 and T2, we will get proton density weighted images. That's an example of how flip angle can affect image. So for example, if I select a flip angle from 5 to 20 with a short TE and long TR, we will be able to produce a proton density weighted images. And with a long TE, I can produce a T2 weighted images or T2 star in this case. That's the effect of flip angle. The larger the flip angle, the more T1 weighting in the image. And keeping the flip angle small and increasing echo time, we will have T2, more T2 weighted images, or in this case, we call it T2 star images. So this comparison between a T1 gradient and a T2 star, both are gradient echo sequences. And the difference is by just selecting a different flip angle and image parameters. So this is comparison between a flare sequence and a T2 star images, or gradient with a T2 star. As you can see, T2 star is really sensitive to hemorrhage. So because of the susceptibility effect, gradient echo sequence, usually they have very high sensitivity to any component of iron. And in this example of hemoglobin, it will show again. And that's another example of knee exam. So on the susceptibility effect is showing more in a gradient echo sequence. And that is a summary of contrast in a spin echo and the gradient echo. And spin echo, a TR should be long. Long means more than 2000. TE should be, again, long more than 60, actually 80 should be 80. Short in a spin echo means less than 700, between 250 to 700, or we can go even to 800. And TE from 10 to 25. Gradient echo sequences, usually we have long means that's more than 100 milliseconds, and a TE is more than 15 to 25. Less than 60 milliseconds is short TR, or even less than 100 milliseconds will be short TR, and from 5 to 10 milliseconds will be long, long TE. So the question, or the last question actually, in the gradient echo sequence, to generate a T2 star weighted image, we should use long TR, short T, and small flip angle, or long TR, long T, and small R flip angle, short TR, short TE, and this is T2. The rule says what TR and T should be usually, just to eliminate the others. We have to, this is T2. We said T2, usually T and TR should be what? Okay, that's the correct answer. It's long TR, TE and TR should be long because this is T2. So spin echo or gradient echo, usually TR and TE should be long. Now flip angle is the only different. If I use a large flip angle, means T1. Give more distance, I can see which runner is faster. And if I give flip angle, I will eliminate T1 and only T2 is dominant. So as at the end of this lecture, we would just mention the MR is not something that can be controlled by one parameter. All these parameters has to be in the picture to produce the best MR images. And we say this is a trade-off. So MR image to produce a good quality MR image, all of the parameters that mentioned, which is signal to noise ratio, resolution, contrast, artifacts, scan time, all has to be considered. So a high resolution image with a low signal to noise ratio is not desired. Again, a high resolution image with a very long scan time is not also desired. Patient can move and he can destroy all of your work. For example, if you can take number of averages high, but the patient will move, again, will not be good. So patient motion is a challenge. So bear in mind resolution, signal to noise ratio, but again, don't forget that patient might move and you will lose everything. A good image is the one where all parameters is optimized. And this is, for example, spatial resolution, signal to noise ratio, artifacts, scan time, all contrast, all should be considered in the image. This is again the last slide. All of these parameters are combined to produce the final MR images. So all has to be in mind. So using a new MRI sequence and technique can reduce scanning time and improve image quality. And that's why people work with MRI have to be always in close contact with the new development of technology. As whatever we mentioned in this lecture, this was the basic theory, but nowadays there's a lot of modifications, a lot of techniques, can reduce scan time, can reduce motion, can improve signal to noise ratio, but the basics are always the same. Thank you so much for your attendance, and really sorry if I did not answer any of the things that in your mind, but as I said, we try to give the basics parameters of MR images. We will try to answer some of the questions as we can see. One of the questions, the first question, to any degree, MRI give evidence that a person is infected with COVID-19. Sorry, I cannot answer this. I'm a medical physicist. You have to ask a radiologist for this question. I am a pharmacist. Some patients may come to pharmacy and ask us about MRI report to check on their health. How can a pharmacist help them this assured for I think they should ask their doctor. As pharmacist, maybe will not be able, as a medical physicist, I can sometimes, although I have an experience of MRI, and I cannot answer some questions, I cannot interpret reports, but I mean, they have to be referred to their physician. Let us select some of the questions quickly. I said some vendors, let's see if I can just move quickly. Some vendors have RF amplifier built in the array coil. How does that affect signal to noise ratio? This is a good question. Again, as I said, whatever we mentioned in this lecture was a theory-like. There's a lot of modifications. The idea is try to reduce the noise. So instead of having that chain from patient, RF coil, wire, and then a preamplifier, so all these will add a noise to the signal. So instead of making this chain long, if you try to cut this chain and put the preamp inside the coil, that will make a huge improvement on the signal to noise ratio because you cut part of the noise. It isn't a good idea. So, but again, this is the technology. Here's a lot of questions. Why we need to, 1 second, please. I can just, what kind of contrast agent used in MRI to enhance the images? And what we mentioned in this lecture is natural contrast, means the contrast that is based on T1, T2 proton density. Sometimes those are not sufficient. So we inject a patient with contrast. There are two types of contrast in MRI. One is working on a T1 and one is working on a T2. Said the T1 contrast will make the recovery of the blood faster, and accordingly, so instead of showing the blood black, short recovery, it will show a bright, like the blood will become very bright like a fat. So enhancing areas where the contrast can pass blood-brain barriers, so it will enhance and show bright using a T1 contrast. T2 contrast based on iron components. So if you inject them, they will make susceptibility effects surrounding the contrast, and there'll be a drop of signal. And so it's opposite to T1. T1 based on highlight will be bright. T2 star or T2 contrast will show susceptibility effect and less signal. If we use a gradient echo sequence to reduce the scan time, why we need to use a large flip angle in T1 image? I think we answered that through the lecture. T1 will make the contrast in a gradient T1 contrast. I mean, it's not necessary to use a very large flip angle. We can use 60 or 50 even flip angle. Still, we can see this is a T1, and we can make a time short. And this is the idea in a gradient echo sequence. The smaller the resolution value, the higher the resolution. Maybe he means the better the signal to noise ratio. The smaller the voxel size, the higher the resolution. This can be correct like this. Could you please get... one question about the protocols. Standardizing the protocols in the hospital, I think this is not maybe, because it depends on the type of radiologist. Some radiologists depends on the, and especially in MRI, every day we have a new techniques and new modifications. So really it is not a good idea to standardize the protocols, because it's varied from hospital to hospital, vary of the type of patients they see in that hospital and compared to the patients seen in the other hospital. Does the calibration after the localizer has any role in signal to noise ratio? As far as I know, calibration is necessary in the new techniques like parallel imaging. They use the calibration to make the scan time faster and to fill part of the case space. And some of the calibration, if I understand the calibration, sometimes you can hear some clicking on the magnet before starting the scan. It is used to tune the coil and the gradient before starting the scan. Can you prescribe both T1 and T2 for one patient? I mean, MR sequence, usually a protocol consists of number of sequences, usually axial coronal stages and also T1 images, T2. So it has a different, for example, a sequence with a T1, another sequence with a T2, another one with proton density, flare, and so on. That's why scan time in MRI is a bit longer than CT or other, because it's actually a series of images. I think that is the time will allow us to answer. If I can, you can get my email. just type my name in the Google and they can get my email. If anything I can answer it, I'll be more than happy. Again, thank you so much really for attending our lecture today. And I apologize if I did not cover a topic that in your mind, and MRI is really expandable. It cannot be covered all in one topic. And also I can feel if you just come to attend that lecture without a prior knowledge of theory of MRI, it's really difficult to understand what I'm talking about. But at least we at least gain some of the information. Hopefully you can, by reading, you can enhance your information more and more. Mr. Ghassan?
Thank you so much, Dr. Abdullah, for this valuable webinar. I really appreciate it for accepting our invitation from Mrs. Marti. Thank you so much for Dr. Abdullah. And also on behalf of SMRT, I want to thank all of the attendants from inside and outside Saudi Arabia who attend this webinar. And I'm happy to announce that the attendance number reached more than 9,000. Thank you so much for everyone to attend this webinar. And also I want to encourage everyone to follow us on our Twitter page at Saudi SMRT to find all upcoming events and webinars, and also the Saudi Commission for Health Specialties page. Thank you so much, everyone. And SMRT is happy to announce that the next webinar subject will be contrast media enhancement and ultrasound. The date and time will be announced so soon, inshallah. And finally, I want to thank Saudi Commission for Health Specialties, especially Ms. Ghada and Mr. Muhammad and Ms. Bayan for their outstanding organization of this webinar. Thank you so much, everyone. And thank you so much for all the attendance again. We really appreciate it in SMRT. Thank you so much and good night.